Okay, let's talk about some guidelines for graphing rational functions. Rational functions that are not simple transformations of 1 over x or 1 over x squared can be graphed using the following procedure. F of x, of course, is p of x over q of x. P and q are polynomial functions with no common factors to factor out and cancel. Step number one, determine if you have any symmetry. If f of negative x is the same as f of x, or f of negative x is negative f of x, you might have y-axis or origin symmetry. Well, remember, look at all your exponents. If all exponents are odd, it's an odd function and origin symmetric. If all exponents are even, it is even function and y-axis symmetric. Adding or subtracting constants will mess up an odd function but not an even function. Step 2, find the y-intercept if there is one. Find f of 0. Find the x-intercepts if there are any by setting the numerator, p of x, equal to 0. Find the vertical asymptotes by setting the denominator equal to 0. Find the horizontal asymptote, if there is one, by using the rule to determine horizontal asymptotes. Plot at least one point between and beyond each x-intercept and vertical asymptote. Use the information to graph the function between and beyond the asymptotes. All right, seems like a lot of work, but it's usually not too bad. Step number 1, if there's symmetry, that can be useful in graphing. What I see are x to the first power, so right there we have odd, all exponents are odd, but we have plus or minus constants which mess up odd symmetry, so we have no usable symmetry. Number 2, y-intercept, or f of 0. If I plug zeros in, my numerator becomes 0 minus 1, which is negative 1. Denominator becomes a 0 minus 1, which is negative 1. So our y-intercept is positive 1. I'm going to put a dot there right now. Number 3, x-intercept. The x-intercept is where the whole function equals 0, and the whole function is equal to 0 when just the numerator is equal to 0. So I'm going to set 2x minus 1 equal to 0, and I will add 1 to both sides and divide by 2. So x equals a half is our x-intercept. I'm going to put that on the graph right now. Get over there. Step 4, vertical asymptotes. Vertical asymptotes is where the denominator equals 0, or x minus 1 equals 0. That tells me I have a vertical asymptote at positive 1. I'm going to draw that in the graph right now using red. So we can start to see a little shape of the graph. Number 5, horizontal asymptote. And we use our rule. I see a tie, x to the first in the numerator, x to the first in the denominator. So we use our leading coefficients. 2 over 1 equals 2, or y equals 2 is our horizontal asymptote. So our asymptotes are falling into place. Step number 6 is plot some other points in between the asymptotes and the x-intercepts. So I'm going to come up here to do my number 6. I'm going to plug in some x values and see what values pop out of our function, f of x. And we want to do it in between the asymptotes and the x-intercepts. So as I scan along my x-axis, I first hit this x-intercept at a half, and then I hit the asymptote, and then I got beyond the asymptote. So let's see here. Let's try a number. I guess we could plug in a negative 2, right, and see what happens. Ooh. If I plug in x is negative 2, I'm going to get my numerator will be a negative 4 minus 1, which is a negative 5 in the numerator. And then the negative 2 minus 1 is a negative 3 in the denominator, or positive 5/3, or 1 2/3. So I'd be right about here. And we do know that 2 is an asymptote, horizontal asymptote. So this part of our graph looks like this. Now we got to figure out where we are beyond the asymptote. Maybe we'll be up here, maybe we'll be down here. Let's plug 2 into the graph, or into the function, excuse me, 2. If I plug a 2 in the numerator, I get 4 minus 1 is 3 in the numerator, and 2 minus 1 is 1 in the denominator, so I have the point 2 comma 3 over 2 up 3. We could plug in some other points, but after you do enough of these, you'll start to get a feel for the graph. It's going to look kind of like a reflection of what we see down here. There's our graph up in the first quadrant. All right, that was fun. So that was a simple reciprocal function there. In the next and last example, now look, we have our x's are squared in those numerators and denominators. First, symmetry. Is there any usable symmetry? I see all exponents are even exponents, and constants can shift you up and down, and that does not mess up your y-axis symmetry. So it's an even function. We are going to be symmetric on the y-axis. When we plot extra points, that will be useful. Number 2, y-intercept. I'm going to plug a 0 in for all x's, and I'm going to get 0 over negative 4, and that's equal to 0. Y-intercept is 0. Number 3, x-intercept. Set the numerator equal to 0. When the numerator equals 0, the whole thing does. When I set 3x squared equal to 0, I get x equals 0. Same dot. Number 4, vertical asymptotes. Look at that denominator. Where would that denominator equal 0? You could factor it here into x plus 2x minus 2, or you could add 4 to both sides and square root. Either way, x equals plus or minus 2 are vertical asymptotes. And let's put those in right now. There we are at positive 2. Ooh, another one here at negative 2. Step 5, horizontal asymptotes. I see it's x squared in the numerator and denominator, so it's a tie. So I look at my leading coefficients, 3 over 1, and that's equal to 3. That's a terrible 3. 3 is my horizontal asymptote. Step 6 is some other points. Other points in between the asymptotes and the x-intercepts. So I like to work my way along the x-axis until I hit an intercept or an asymptote. So if I'm over here working my way to the right, negative 2 is an asymptote, so I want to check a number to the left of that. Well, to the left of negative 2, let's try negative 3. I'll plug a negative 3 in for x, and I'll square that and get a 9 times 3. That numerator is a 27. Denominator will be negative 3 squared is 9. 9 minus 4 is 5. 27 fifths, or about 5.4. So there's a point, negative 3, comma, 5.4. So I know I'm up here. And if these are asymptotes, and also the symmetry around the y-axis, I know I'll have a point over here. Oh, I could check a couple more points, but if you know you're in this box, boxed off by the asymptotes, it's going to look like this. Okay. Let's see here. What's going on in between negative 2 and 0, between this asymptote and the x-intercept at 0? Well, let's plug in a negative 1. If I plug in a negative 1, it'll be the same thing as plugging in a positive 1 because of the symmetry. 3 times 1 squared, that numerator is a 3. 1 squared minus 4, that'll be a negative 3. 3 divided by negative 3 is negative 1. So at 1 and negative 1 on the x-axis, I'll be at negative 1 on the y. So that's enough to tell us we got sort of like a parabola, open and down, in between the 2 and negative. Ooh, I touched that asymptote. Can't do that. There we go. That's a little better. And that's it. The graph is represented somewhere except at the vertical asymptotes at 2 and negative 2. Okay, for practice, checkpoint 5, that's just to the first power, and the next one, checkpoint 6, is the squared power. use the 6 or 7 step process to graph those. Okay, for the first one, symmetry, they are all odd exponents, but we have plus and minus some numbers, so there is no usable symmetry. 2, Y-intercept. Plug a 0 in for all x's, and you'll get -3 over -2, or +3 halves. +1.5, put a dot right there. 3, the X-intercept. Set the numerator equal to 0. 3x minus 3 equals 0. Add 3 and divide by 3, you get x equals 1. X-intercept of 1. Number 4, vertical asymptotes. Set the denominator equal to 0 at x minus 2 equal to 0. X equals 2 is a vertical asymptote. Ooh, that was supposed to be red. There we go. 5, horizontal asymptotes. It's x to the first, x to the first. It's a tie. So we use the leading coefficients. 3 divided by 1 is equal to 3. Horizontal asymptote at y equals 3. Number 6, we need some other points in between the x-intercepts and the asymptotes and beyond. So let's see, over here to the left of the x equals 2 asymptote, I do already have a couple points there, and I can sort of see how this function's behaving. I know it's going to sort of look like this. Ooh, that wasn't very good. I can do better. No. There we go. That's a little better. Okay, and then we hit the asymptote at 2, and on the other side, what's going on here? Is our function in this part of the graph, or is it up here? Let's just do a point to make sure. We could plug in a +3. If I plug a 3 in, I'll get 3 times 3 is 9, minus 3 is 6. That's my numerator. 3 minus 2 is 1. So 3 comma 6 over 3 up to 6. And what the heck, let's put in a 5. 3 times 5 is 15, minus 3 is 12. 5 minus 2 is 3, that's our denominator. 3 divided by, or 12 divided by 3 is 4. 5 comma 4 is a point. Over 5, up 4. And there's some more of what our graph's going to look like. All right. Checkpoint 6. Now here, the big difference is it's an even function. We have our even exponents. Constants do not mess up even symmetry. So we have even or y-axis symmetry. Two, y-intercept. If I plug a 0 in for all x's, I'll get 0 over -9 or 0. 3, my x-intercept. If I set my numerator equal to 0, I also get a 0. So I'm going through the origin. Number 4, vertical asymptotes. What would 0 out my denominator? X squared minus 9 will equal 0 at positive and -3. So at 3 and -3, I have my vertical asymptotes. Step 5 are the horizontal asymptotes. That is, I see my x squareds, it's a tie in the numerator and denominator, so my leading coefficients are 2 over 1, or 2. There is my horizontal asymptote. Now we just want to find out where the function exists between the asymptotes and the x-intercepts with some extra points. See, we got this point right here at the origin. Let's try 1 and -1 on either side of it. Because of the y-axis symmetry, you know, these will give the same output, plus or minus 1. Let's just do the positive one. So I'll get 2 times 1 squared is 2 in the numerator. And then I'll have 1 squared is 1 minus 9. 1 minus 9 is negative 8. So I get negative a quarter. So at 1 and negative 1, I'm down here. And that sort of makes sense because of the vertical asymptotes at 3 and negative 3. This part of the graph will be a parabola opening down. Okay, we got to see what's going on here. Let's try minus 5. If I plug in the minus 5, it'll be the same as the plus 5, again, due to the symmetry. So if I plug in a 5, that'll be 5 squared is 25 times 2 is 50 in the numerator. And then 5 squared is 25 minus 9 is 16 in the denominator. And that's a number a little bit more than 3, 3 and an 8. So if I go over to 5, I'd be at a number just a little bit over 3. I get over there. And also here, and that at least tells me I'll be in that quadrant, and I cannot cross the asymptotes, so it'll look something like this. Okay, I believe that's it for this video. Homework is page 407. I'm sure you're going to be graphing a few of those. Don't forget to ask me for some graph paper.